The real number line has one dimension, and we can graph real numbers on it because what real numbers have one dimension also. So if I wanted to graph the number 3, I just need to draw the real number line, 1, 2, 3, and there it is graphed. So a relation is a set of connections between two sets. And this is called a binary relation because it's between two sets. And that's really what we're going to be working with. Now, these sets are going to be paired numbers. So it's a set of numbers going to a set of numbers or connected to a set of numbers. And each set or each pair of numbers is called an ordered pair. We're also going to call them coordinates. Ordered pairs are in the form x, y. It has the parentheses, x comma y parenthesis. X and y are just real numbers. And this ordered pair has two dimensions. Each number is one dimensional. So if you have two of them, that makes it two dimensional. It's important to note that this notation is not an interval. It looks like an interval, but it's not. Context will tell you whether you're working with ordered pairs or intervals. In this case, we're just working with an ordered pair. So a relation can be listed as just a set of connections. Here we have 1, 2, 3, 4, 5 connected numbers. And because I can count it out, this is called a discrete relation. There's 5 things in here that makes it discrete. And this relation just has 6 is connected to -7, 3 is connected to -5, 7 is connected to 7, -5, -5, and 3 to 2. I haven't told you why they're connected or anything like that. I just told you the connection. Now we can analyze relations of various kinds using the Cartesian coordinate system. And this system is it's quite clever. It's just two real number lines. Attached at a right angle, and the right angle is a key thing. That's what makes what this Cartesian coordinate system rectangular, which that's not really important right now, but also because there's two real number lines, it's a two-dimensional coordinate system. Now the horizontal real number line will be called the x-axis, or the independent axis. The vertical axis would be called the y-axis, or the dependent axis. And of course, these things can be flipped. The variable x and y can be changed. If we're talking about like dollars per hour, then the independent axis, the horizontal one, will be a t, probably t for time, and the dependent axis, the vertical one, will be probably dollars, a dollar axis. Now, where the two axes intersect, you have the origin at point 0, 0. And this is kind of a starting place of the entire coordinate system. It's an important point to always kind of keep in mind where it's at. Now, with these two things, we create this Cartesian coordinate system that I have here. And you can see that these two axes cut the place up into 4 quadrants. And we always start with the top right. This is quadrant 1. Quadrant 2, you go counterclockwise, and you get quadrant 2. We always describe them using Roman numerals. So 1, 2, then we have quadrant 3 down here, and finally quadrant 4 right there. Always this counterclockwise motion. Now in this top quadrant, in quadrant 1, we have positive x values on the x-axis here. This is the x-axis. This is the y-axis. So we have positive x values. You can see you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Positive x values, and then positive y values going up. So this is quadrant 1. Quadrant 2, we have negative x values going this way, and positive y values. That's all in this quadrant. Quadrant 3 has both negative x and negative y. And then quadrant 4, positive x and negative y. Okay, using this kind of idea, we can ask certain questions about this thing. Like, for instance, which quadrants have x cubed less than 0 and y cubed greater than 0? So to do this, all we really have to know is look at these things and say, well, what we're really looking for is when are these things positives and negatives. So if we plugged in a positive x into x cubed, we would get positive x times positive x times positive x, which of course is just positive x cubed. But this is greater than 0, right? If you plug in a positive x, you get a positive x cubed, and that's going to end up being greater than 0. That's not what we want. We want less than 0. Well, let's just double check to see if negative x cubed gives what we want. So we get negative x times negative x times negative x. This is going to be a negative x cubed. And so if you plug in a negative number, you'll get a negative number out. And that is less than 0. So we're looking at negative x values, and that's going to be in quadrant 2 and quadrant 3. Those have these negative x values here. Now for positive y, we can do the exact same idea here. And you can see that positive y's will give us positive y's out. So we want to have negative x's, and we want positive y's. Well, the quadrant that has negative x, positive y is quadrant 2. So that's the only quadrant that has these kind of specifications. Now, we can plot ordered pairs using this Cartesian coordinate system. The way we do this is we first look at the first number in the coordinate and go left or right to it. So the left or right to the first number on the x-axis. And then from where we find that first number, we go up or down to the second number on the y-axis. And we just put a dot on that one location. So for instance, graph ordered pairs negative 2, 4. Well, negative 2, 4. Negative 2 is right here on the x-axis, right? Negative 2 is just right here. And then we go from this point up to 4 on the y-axis. The y-axis of 4 goes here. So from this point we go 1, 2, 3, 4. That is the location of the first coordinate. So we go ahead and show this in Desmos. Negative 2, 4. And you can see that is exactly what we found. Negative 2, 4. Okay. The next point is 4, negative 2. So 4, negative 2 is 4 is right here on the x-axis, right? 4 is right here. And then negative 2 is going to be down here, 2 units down. That's negative 2 on the y-axis. So 4, negative 2. Okay. We plot that point. Okay. Negative 3, 0. So negative 3, 0. Negative 3 is going to be right here on the x-axis. Always go left or right first. And then 0 means we do not go up or down at all. We just stay right there on the x-axis. So negative 3, 0 is right there. Mark that with a spot. Negative 3, 0. Just right there. 0, negative 3. 0 means we do not go left or right at all. We just stay here on the origin. And then we go down to negative 3. So 1, 2, negative 3. be right there on the y-axis. As you can see. And finally, we have 5/3 and 9/2. So 5/3 is 1 1/3. 5/3, so 1 and then, sorry, 1 2/3. So 1 2/3 is just about here on the x-axis. Then from this point, we're going to go up to, I think it was at 9 halves. 9 halves. 9 halves is 4 1/2. So 1, 2, 3, 4, and then halfway up, it'll be just about there, somewhere around that spot on the coordinate system. So go ahead and plug it in. And there it is, 1 2/3, and then 4 1/2 right there. So that's how you can graph points, any kind of relation on a coordinate system. Just go left or right, then up or down, and that'll give you the point. Go ahead and try this out on 1 and 2. Okay, so we're going to graph this relation. I had shown it before, but we're going to graph this relation. I'm going to graph it three distinct ways. So the first way is I'm going to create some balloons. And the balloons are going to be, I'm going to look at the first values, 6, 3, 7, -5, and 3. 3, 7, -5. And again, we have 3, so that's right there. We can think of this first balloon as a set, kind of like a Venn diagram set, but now we're not going to be using Venn diagram as a normal thing. I'm just going to graph the set using a balloon. Now the other set I'm going to draw is the other values. -7, -5, 7, -5, and 2. So -7, -5, 7, -5 again, so I'm not going to draw it a second time, and then 2. And now to actually graph this relation, all I'm going to do is I'm going to draw arrows making or showing the connection between the two numbers. So 6 goes to -7, 3 goes to -5, 7 goes to 7, -5 goes to -5, and 3 goes to 2. And that is a graphed relation. Now, a different way of graphing this is going to be what's called a table of values. I'm going to write it like this, x and y. And the reason why I'm writing x and y is because we always think of these ordered pairs as x comma y. So the first values are the x values, the second one is the y. So we have 6, 3, 7, -5, and 3. 6 goes to -7, 3 goes to -5, 7 to 7, -5 to -5, and 3 to 2. Now this is pretty much the exact same thing as the set. However, when you're looking at relations, this table of values is probably more common, what you're going to see for a graph of a relation. We don't usually use set notation like I have here in the very beginning. We don't really use this notation to show a relation. We will normally use this table of values or this next method, which is just to graph all of the points on a Cartesian coordinate system. So if I do that, this is the relation right here. It's just these points. Once again, I haven't told you why these numbers are related this way. I've just told you that they are. Now, each one of these kind of shows different ways of thinking about a relation. With this first relation here, this first graph, these values, this first balloon, 6, 3, 7, and -5, this is the domain of the relation, or it's all the independent values that the relation runs through. It's the same thing as the x values, you just don't allow repetition. Now in the right oval is the range, or independent values, or sorry, dependent values. It's all the y values, and it's all the values that the domain connects to. It just goes from the x to the y, and that's going to be all the y, all the range values. So the domain of A, like I said, is just the set 6, 3, 7, and -5. And the range is just the set -7, -5, 7, and 2. So give this a try in 3 and 4. Okay, the final relation I'm looking at here, this is also a discrete relation. The previous ones I've shown you have been relations that have been limited, but this one is infinitely long. You can see it's because it has the ... right? It continues indefinitely in both directions. And it's still discrete, however, because I can count them. I could say this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7, then 8, then 9, then 10, 11. So that still makes it discrete. However, this is an infinitely long list of ordered pairs, I should say. And all we're looking at here is what is the domain and range. Well, if I graph these values, I can graph them like this, and we can see that this is what it looks like here. And because the ... dots are there, that means we can think of this pattern continuing indefinitely. And hopefully you can see the pattern here. -2 goes to 5, so -2 goes to 5. I've actually graphed one more, 0 going to 6. That would be one right before that. But -2 goes to 5, 0 goes to 4, 2 goes to 3, 0 goes to 2, -2 goes to 1, 0, 0, 2 goes to -1, and the next one, it will be that one, and then here, and then here, and then here. And you can see this pattern is just a zigzag across these values. And it keeps going downward, and it keeps going upward like that. So we don't actually need to know what the rest of the values are to see the domain and range. The domain are going to be all of the x values that it runs through. Well, you can see that directly from this list of values, we have -2, 0, 2, 0, -2, 0, 2. Next one's going to be 0. The next one's going to be -2, and so on and so forth. It only ever hits those three values: -2, 0, and 2. The range, well, if we look again at these numbers, we have 5, 4, 3, 2, 1, 0, -1, -2, -3, -4, -5, -6, -7. And going the other way, we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So you can see that the range is just going to be, I'm going to write like this: -3, -2, -1, 0, 1, 2, 3. That's the range, but this is the same thing as the integers.